Yes, yes, tell me.
I hope now you are better because I spoke to you last. Yeah. Sir, actually, I just wanted curious, like, sir, what actually do you teach in Cambridge? Like, what do you teach?
Look, I'm at present an emeritus professor.
Okay.
I just design the lectures, and I just interact with students.
Okay.
There's no formal teaching as such. So if any student is interested, right now I have 3 students who come and we are discussing, and I'm giving them a formal course in alternative cosmology.
Okay.
The research students.
Okay.
So
Okay. Sir, if I am not wrong, like you were earlier as a student of Delhi University, and from there, like you went to Cambridge. Like how I didn't knew much about that. So if you can just tell me, like from Delhi University to Cambridge, like it was a journey.
Yeah. So I was in the University of Delhi. I had actually had an accident. Did I tell you this?
No, you never told me.
When I was in the final year, I had an accident, and I was in the hospital. I gave my final year exam in the hospital itself.
Okay.
So at that time, when it came to particle physics and field theory, I wrote a dissertation in general relativity. And so while I was doing that, I just posed the question. It fascinated me that the way one defined a particle in field theory depended upon the kind of basis function we were choosing.
Okay.
And so I was wondering whether the basis function chosen had some kind of a normalization in a large box which is large as compared to the dimension of the apparatus.
Okay.
I just posed the question on whether if the box was really comparable to the size of the universe and was escaping from the horizon of the universe.
Okay.
So whether the definition of a no particle state, that is a vacuum,
right,
what it would translate in terms of a vacuum which is defined in a box which is much smaller than the size of the universe.
Okay.
So it turned out that the previous state was a thermal state.
Okay.
And I determined the temperature. So this paper I had sent for publication to Physical Review.
Okay.
And this was noticed by Stephen Hawking.
Yeah.
And that's how I landed up in Cambridge.
Okay. So, sir, like, do you come down to India, or you are permanently over Cambridge?
No, I'm a life member of a constituent college here.
Okay.
That's the way it works. All faculty members are members of some college. So I'm a member of Clare Hall.
Okay.
And I went and, there's this research scientist scheme that I was also responsible for creating the scheme.
Okay.
So it was a University Grants Commission scheme in which people were selected centrally and placed in universities of their choice in the same grade as lecturers, readers, and professors.
Okay.
So I joined that scheme, and I was in the University of Delhi.
Okay.
So I came into the professor's grade in 1994, and since then I kept, however, Cambridge allowed me to keep coming back, so I kept my position in Cambridge as well. Back.
So right now you are at Cambridge talking to me?
Right now I'm in Cambridge, not permanently. I'm here till the end of August this year.
Okay. Sir, one thing really fascinated me, like the paper that brought the attention of Stephen Hawking, and then you further expanded on that area. So just wanted to know the students now who are closely associated with you, where you are providing them, interactions and regarding cosmology. So after the initial talk that you did with me last time, I was also thinking that when you applied this, as you told, to black hole, and which was later applied to the function or this to the entire universe by Stephen Hawking. So further papers, like, I don't know, I was very keen to read, like, is there any archive or any email where this work has expanded on a larger scale, where you have worked on this black hole emitting particles, or how is that? I was just willing to know.
The work that I did, I did derive I have a letter from Stephen Hawking which says that, that he is impressed. I'll quote the letter, that he's, dear Mr. Daksh, Esquire, I'm impressed that you've discovered the thermal properties of the distant universe entirely on your own. And the letter continues. Now, I did not realize the importance of the result, I must admit. And, so those thermal properties are supposed to be the seeds, or those fluctuations are supposed to be seeds that then develop into that are responsible for structures on large scale.
Right.
All right. So this is it's very important in inflationary universe, in inflationary cosmology.
Right.
So the universe is supposed to have undergone an inflationary expansion.
Right.
It's also called the dissident expansion. So the fluctuations at that time later developed into galaxies. So there is no other ansatz at present. So, so that was important, and I didn't know about that at all.
Okay. Sir, one thing, like, I just wanted to know, I read about this, but I just wanted for a person, great expert like you. Often and on, when we read things about black holes, typically, it states that black holes are a solution to Einstein's field equation. Now, what I'm trying to understand from you, sir, say, for example, given a solution or an equation that it will, given a value of x, the equation will give out the result there. Now, if I consider the Einstein's field equation, the left-hand side and the right-hand side with all the Ricci tensors, metric tensor, Ricci curvature, everything, correct me if I'm wrong, like, I want to know, like, given, for example, a star, which is non-rotating, and given this property, mass, energy, density, spin, etc., I plug in those values in the Einstein field equation and then solve it, and then what I get is an infinite curvature and density, which in literal terms mean black hole. Is this actually is meant by the solution of Einstein's field equation?
No, you see, I'll just tell you, this is not the way we, Einstein's equations by themselves are really incomplete, and Gödel pointed this out.
Right.
So the point is that Einstein's equations tell you that there's some connection between stress energy density and the basic geometric properties of the underlying space-time.
Okay.
Now, the thing is that you cannot treat the Einstein's equations in the following manner: that given a stress energy distribution, you can find the geometry.
Okay.
No, because to specify the stress energy distribution, you always already have a notion of space-time. You get the point?
Yeah.
If I say that I put 10 grams of mass there and 20 grams of mass at some other point and so on, so which means that there is already a pre-geometry. This is not the way it works. The way it works is that so you need geometry already to specify the distribution, and you need the distribution to specify the geometry. So there is some kind of a interrelation, but you cannot solve it that way. So what you do is you have to take this loop. So you ask, what is the most general spherically symmetric solution?
Okay.
So you put in an extra. I wonder if you know Gödel's inconsistency.
Yeah. I have read Gödel's incompleteness, and in Princeton, he pointed out Einstein that
if I say that I live opposite your house And where is your house? Well, it is opposite my house. Where are both the houses? They are opposite each other.
Right.
So it doesn't get you anywhere. You have to put in something else.
Right.
So the something else here in Einstein's equations, the way you do is what you do is you put in symmetry, which is not there in the equations a priori. So you ask the question, what is the most general spherically symmetric solution? So you write down the most general spherically symmetric metric, and then plug it into Einstein's equation. And what you find is, and you solve them, and you find that only one parameter, which is this m, and that specifies the entire geometry. That's a solution. Now, if you consider trajectories in this metric, so you consider geodesics. They're called geodesics. You consider geodesics in this metric, you find that their three-dimensional projection resembles planetary or other orbits.
Right.
Parabolic or hyperbolic, depending upon the initial conditions of the particle whose trajectory you are trying to determine. And so that m, that parameter, is interpreted as a mass at the center for spherical spin. So you assume that the sun is a center for spherical symmetry, so that is outside the sun is spherically. If you assume sun is spherically symmetric, then outside the sun you have, or outside a star, there's vacuum. So you consider the most general spherically symmetric solution, with m being the total mass of that spherically symmetric distribution. So you can also solve. You can do. If you know the equation of state, if you specify the equation of state of the matter inside the star, you can solve that also. That was done by Oppenheimer and Volkov.
Right. So,
by their name.
Why this? Let's say, for example, Schwarzschild radius. It is called. It is a solution to Einstein's field equation. So,
so the first person who discovered this solution was Schwarzschild. Do you know his story?
Story like he was in First World War. That's all.
Yeah. He was in the First World War, and he was in a trench, and he was hit by a shell, and he later died. But before he died, he wrote down this first solution, which goes by his name. It's an amazing story.
Okay. So,
anyway,
as you told,
solution.
Right, sir. Tell me. Sorry.
What were you asking? So it's a Schwarzschild solution, basically. But the Schwarzschild solution for a distance which is much larger than what is called the size of an object, the spherically symmetric object.
Right.
Is much larger than what is called the Schwarzschild horizon.
Right.
Then the geometry outside that object will be the same as the geometry of the Schwarzschild solution for that distance.
Right. So, like as you were telling, sir, with an example that if I put a 10 gram of iron over there and 20 grams of a football over there, then we already have a geometry, and which is not correct.
Yeah, this is not the spirit of Einstein's equation. So what you can do is you can do an iteration procedure. You could just specify background geometry, and then perturb it, and then carry out iteration procedure. You derive the change in the stress energy tensor due to the interaction between the gravitational interaction between these particles. Then add that change to the source. Then do another approximation, and then add that as well. So this iterative procedure you can carry out.
Okay. So, I believe it is quite complicated to derive a Einstein's field equation given the boundary given the condition. Like, is it so?
You see, with a computer you can derive. You can carry out this procedure, but to derive an exact analytic solution, it has been done only for very special cases. it's been done for the spherically symmetric case, which is a Schwarzschild black hole. Schwarzschild solution. When you have if you have a spherically symmetric distribution with a charge, that's called the North-Storm solution.
Okay.
Then we have if a charged object is rotating.
Right.
If you also have an angular momentum, it's called the Kerr-Newman solution.
Yes, Kerr metric, right.
And then you have. Yeah.
So, sir,
so there are lots of other solutions. They are called Bianchi solutions.
Right. Bianchi solution. Right. So, sir, what is called an exact solution?
Oh, an exact analytic solution. You find a solution in terms of a closed formula. So it's an analytic formula rather than a numerical solution.
Okay. Sir, one thing I was reading, after the first meeting when you told more about Michael Atiyah, I went on reading about him. In one of the interviews, he was telling that the same chord which strikes and appreciates music also appreciates mathematics. So I was reading
what he meant.
Yeah, I was reading Michael Atiyah. So, if you can share your interaction with Michael Atiyah, how did you what was the talk and a few words about that great person?
Well, he was very thorough, and he was not. He related to physics a lot more, but pure mathematicians.
Okay.
They are in the world of their own. They don't need. See, whenever you a normal mortal studies pure mathematics, whenever I did pure maths, I always made some kind of a model in my mind.
Okay.
And then looked at the structure in terms of that model.
Okay.
So that's how I would do topology. That's how I do. So it won't just be abstract algebra.
Okay.
But the real pure mathematicians, they don't need any model to support them. They just have to believe in that abstraction. So that training is something that, and that knack of appreciating that is something that I had some 40 years ago, and then I because of lack of use of it, I lost it. So Michael Atiyah would be a person who would live in both ways. I mean, he could talk to pure mathematicians, and then as well as he would know how physicists understand things. So he would make models.
Okay.
So that was great.
Okay.
So my interaction with him was on a theorem. There's a paper that he wrote with Singer and Patodi. So he was this Indian mathematician.
Right. Yes.
So the theorem goes by the Atiyah, Patodi, Singer indexer.
Okay. So, he is basically a pure mathematician, Dr. Michael Atiyah.
Yeah, I think he's no more.
No, he has expired. Right. Sir, have you met Dr. Andrew Weil?
The name is very familiar.
The person who proved Fermat's last theorem. It was way back.
Okay. No. I know who you are talking about. Yes. No, I attended his lecture, but I don't know him.
Okay. And Dr. Gary Gibbons, I think you are much closer to him.
Yeah, of course.
Okay. So, Professor Gary's, I think, it would be an awkward question to ask, but still, he has been a profound influence in terms of everything that, from the basis and the developments, etc., the way mentoring happens in your...
Yes.
So he has been like a father. I mean to say, somebody who has mentored you. More than Stephen Hawking.
No, it's been almost the same.
Almost the same. Right.
Yeah.
Sir, one thing which kept me thinking that whatever the researches that are going on, say in quantum cosmology or things, that what is actually preventing us, or what is the obstacle to find a theory of everything?
So these two are very different things. When you look some cosmology, the point is that people, there's no consensus on what they'll call a theory of everything.
Okay.
What is preventing? You have many models, many proposals, but all of them. You see, the thing is that the scale, the grand unification scale, is about 10 to the power 16 GeV.
Okay. Yes. Yes.
All right. So the amount, the energies that are accessible are just a few trillion electron volts. That's the accelerator.
Right.
So there's a huge gap. There's a tremendous gap between the energies that are accessible now and the energies needed to, verify really the domain of quantum grand unification scale, and then quantum gravity. The scale that quotes are about 10 to the power 19 GeV.
10 to the power 19, right. Right, true.
So the thing is that it's first of all, to actually verify all these, so the actual verification can only depend on model building. And provided we have a correct theory of quantum gravity.
Right.
Now we don't have there's no consensus on the right theory of quantum gravity. The standard field theory doesn't have any prescription to account for a graviton. The only consistent prescription comes from the string theory. Now, string theory has a consistent account for a spin to quantum particle only if the space-time was 10-dimensional.
Okay.
So now, in a 10-dimensional space-time, you need to compactify 6 dimensions to get for it to reduce to 4 dimensions. And those extra 6 dimensions, the symmetries of those are supposed to manifest as internal symmetries in particle physics. There's no consensus on on the correct compactification scheme till date.
Okay.
So, and then, this is while initially in the mid-80s there was a lot of excitement and a lot of work being done on string theory. It gave a lot of hope, but then it died down because it just there was no consensus. So even I spent about 4 years on string theory, and then I gave up.
Oh, really?
Other things to do.
Was it during that time of 4 years you came in touch with Professor Leonard Susskind, or it was earlier?
No, I never got in touch with him as such. I mean, I read his work, spoke to him a couple of times, but nothing more than that.
Okay, fine. Okay. So it is basically the scale which you're telling, the energy, the level of everything.
Yeah. So it cannot be verified experimentally. So it's just a matter of, you have to have other parameters to test the theory is right or not.
Right. Sir, one thing I like, I watch it in Facebook and otherwise, like there's an International Space Station, ISS, which NASA is constantly sending men and women. Today only I found there's a lady called Christina Koch who has come back spending the highest number of days in International Space Station taking photographs, etc. Now I understand that there has been a huge advancement in terms of technology and everything. But I just wanted to understand, because you are a person who has gone through all those phases. So sending somebody, say for example in ISS, and staying there for about whatever be the tenure, like what is the ultimate gain that mankind or we would gain? Like if we send somebody, he or she stays there, takes photograph and everything, and then he or she comes back. Like how this technology advancement has really helped human solutions, human problems. Can you share something, sir, on this?
Yeah, anyway, there's experience, and then there's a lot of development of spin-off technology.
Right.
that's a leap, and then the thing that, we are just testing our frontiers and what all we can achieve.
Okay.
But the speed of technology is enormous.
Okay. Okay. Right. So, it is basically you are telling that out of those things, eventually something will emerge which will solve out certain problems.
That could not be related at all. For example, in CMB anisotropy, the amount of data that you were getting, most of it was noise. For every 10 megabytes of data every second, there was just about 1 or 2 bytes of the signal, and the rest was noise.
Right.
So we developed statistical algorithms to extract that signal from the noise.
Okay.
And the biggest funder at that time was the U.S. Navy. And we were wondering why the U.S. Navy would be interested in cosmology. They were not.
Okay.
They were only interested in this package. And the reason why they were interested in this package was the statistical package. Was that they knew how to extract a signal from such a lot of noise. So they could just, in cryptography, you could just mix your signal with a huge amount of noise and send it across. And if you knew how to extract the signal, so this would be a way of transmitting signals in war.
Okay.
So look at it's not at all related to cosmology. So you develop lots of techniques, technology, materials. There's a lot of research.
What I was also wondering, I was talking to my father regarding that, huge amount of money is being spent while sending rovers in Mars, which ISRO did, then NASA constantly sending in so much amount. But when I talk, say, for example, the problems of poverty, problems around the world, problems around my own country, around us. So I always used to wonder, to be very honest, don't take me as an offense, I'm much junior to you in terms of age and everything. I always wonder the 10 million, 40 millions amount that which is being spent. Why don't you give this money to the poor villagers? Why don't we bring electricity? Why don't we bring light and food to them? So what I can understand that possibly out of this huge expense that NASA or India or ISRO makes, we can get a hold of something which will definitely benefit mankind. I think you're telling that also.
Yeah, the point is that if we are not being able to provide for the actual solutions to problems in the country, that is not at the cost of other things. If there's a political will and feasibility, so definitely things could be done. And it's either not feasible or there's no political will. So providing electricity, for example, you see, if you provide electricity all over, the system ultimately gets back much more because you can, with the infrastructure development in far reaches, it ultimately contributes to the economy. It's not the consumers who are in the dark are now in the light. They can do something that contributes to the economy,
right?
Even at night,
right?
So you get back that investment. So why were we not doing it? Either it was not feasible, or there were some other political decisions, whatever. So similarly, in other cases, then we also have our 5-year plans. We every successive government has not tried to invest in long-term projects because the dividends and the returns would not help them in the next election.
True.
So all these are considerations.
True. So, even in
for example, the metro, Delhi metro project,
right,
was actually conceived of during the BJP's time, but they didn't get benefit of that. Then it went to the next government. The Congress project was put in place, so it started functioning at that time.
Right. So I really wonder, when I'm thoroughly fascinated. I was watching. I got some time today at office, so I was watching Andrew Weil's interview all those great people who gives interview, the passion, like the type of dedication, the type of madness that they have in order to achieve something, then I personally think that the amount of time and energy, say for example number theory or pure mathematics, that people do involve, and the result, that the outcome that they get, say for example proving Fermat's theorem or proving Poincare conjecture. So I was thinking that really these things will benefit that person who is taking water from the pond, or to that poor people who is living in a hut with no electricity. This keeps on haunting me. Sir, have you completed that writing which you told last time?
No.
Okay.
No, I had said that.
Okay. Because I was thinking to ask you on that, like what we would be waiting for that part. Okay. Fine, sir. Nice speaking to you.
Right.
I will. Yeah. Thank you very much. Bye.
Yes, tell me.